about flux lattices, and this is a topic in its own right. But I just wanted to introduce one last set of facts about Ginzburg theory, which is important if you want to know how to actually measure the coherence length of a superconductor. How do you do that? Okay. Can you go in there and look at the Cooper pairs? Obviously not. One very nice way of doing this is to measure the upper critical field. So I want to talk a little bit about critical fields before we go on and talk about microscopics. So, as I alluded to before, in a simple superconductor, type 1 superconductor, you just have this phase diagram, TH phase diagram, and this is the Meissner phase. And this phase boundary here is a first-order phase boundary. And what determines this first-order boundary is simply when you compare the condensation energy with the magnetic energy of the excluded magnetic flux. And so that's a very straightforward comparison in Ginzburg theory of two quantities. I'm going nuts here because, there it is. And the two quantities you need to compare are the condensation energy, which is R squared over 2U, with the magnetic energy, which is minus mu naught H squared over 2. Really, to do this properly, I'm just going to do it order of magnitude. I'm just going to do it because a careful discussion means I have to talk about the Gibbs free energy, and I just don't want to get involved in that at this point. Comparing these two quantities gives you R squared over 2 mu equals mu naught over H squared minus 2. You basically, this is done by looking at the free energy, actually, which is this quantity here, and comparing the free energy of the normal state with the free energy of the superconducting state gives you this criteria. And this then gives you a critical field, Hc equals R squared over 2U. Okay, and of course R here was A T minus Tc. Okay. But in a type 2 superconductor, you now have two fields. Hc1, which is the top of the Meissner phase, and Hc2, which is the end of the vortex lattice. And you can calculate these two lower and upper critical fields in Landau-Ginzburg theory. It's a longer digression than I have, although it will be in the notes, as everyone says at this meeting. Let me just summarize the key points of the magnetic field phase boundary here. Here is Hc1, and here is Hc2. And these two fields are determined relative to this field Hc. You may remember that we had this quantity kappa, which was the ratio of the penetration depth to the coherence length. And these two quantities are determined by kappa. And so the upper critical field is the square root of 2 kappa Hc2. And Hc2 is determined by a very simple criteria. It's basically when the area enclosed by a circle of radius xi contains one flux quantum. It's more precisely, you get 2 pi xi squared equals a flux quantum. This determines the upper critical field. Okay? So 2 pi xi squared times b C2 determines the upper critical field. So if you know the coherence length, you multiply it squared times BC2. When the field is large enough that this area contains one flux quantum, you can basically no longer form a stable vortex lattice. So this upper this point here is determined by Bc2 equals h over E divided by 2 pi psi squared. And when you work it out, this quantity here, hc2, is the square root of 2 times kappa times hc. Whereas hc1 is basically hc times divided by the square root of 2 times kappa, and a more careful calculation gives you log of kappa. And so experimentally, by measuring hc1 and hc2, you actually have information about kappa. Moreover, this gradient here also gives you important information. Let's have a little look at that. If you accept that Bc2 equals equals h over, we'll put 2e over 4 pi over 2 pi psi squared. If you work that through in our BCS theory, since we know that psi equals the square root of h squared over 2 ma t minus tc modulus, putting that all together, this quantity here can be written as 2 ma tc minus t over E star h bar. And the important point about it is that the gradient of dB by dt, dBc2 by dt, okay, multiplied by Tc, is nothing more than phi naught over 2 pi psi squared. Okay? And so that's a very useful result, because you can measure, even though you may not be able to go to the extrapolation of this to zero temperature, you can get an estimate of the correlation length just by, this is psi naught squared. Remember, psi naught is h bar squared over 2 ma tc. So from this relationship here, you can pull out the coherence length. And by measuring the ratio of hc2 to hc1, you can see that you can get a measure of 2 kappa squared log kappa. It's 2 kappa squared divided by log kappa. So these two relationships give you kappa, and they give you psi. Okay? So, moreover, you can convert this to a handy-dandy formula. If you work out what phi naught is, this is phi naught over 2 pi. This is 10 to the minus 34. So let me write that out. That is h bar over 2e. Okay? That's 10 to the minus 34 over 2 times 1.6 times 10 to the minus 19. And that comes out to be 3.3 times 10 to the minus 16 meters squared per Tesla, which you can rewrite as 329 nanometers squared per Tesla. And so this formula here can be rewritten in the form that it can be rewritten in the convenient form psi equals the square root of 329 over Tc dB by dTc in nanometers. You shouldn't believe 329. 300 is probably good enough, okay? Right? Okay. But these are very useful. Let me give you an example of how this works. Yes?
You mentioned that this is a possible way of measuring, experimentally, the coherence length. That means, how do you vary experimentally
It should be dt. Sorry, Bc2. Sorry, yeah, that's my mistake. Yeah, okay, yeah, okay, right. So that's this gradient here, and there's a minus sign in here. I should put, right, because it's negative. Okay. So to give you this is a very useful formula, and this is also a very useful formula. Okay. So let's just put these formulae up here so we have them. And let me just show you how it works out for a classic type 2 superconductor, uranium beryllium 13. So just to have those there, we have Xi equals phi naught over 2 pi divided by Tc dB by dt at Tc, which is 329 over dB by d log t. You may. Okay, thank you. And
Sorry, this is the T equals 0?
at t equals 0, yes. It's an estimate of it, okay? And the other formula is that Hc2 over Hc1 is 2 kappa squared over log kappa, okay, where kappa is lambda penetration depth over Xi at 0 temperature. Okay, these are approximate formula. To give you some actual data, uranium beryllium 13 is a 1 Kelvin superconductor, in fact, it's 1 Kelvin. It has a very, very high gradient here, and I forget what the upper critical field is, something like about 9 Tesla. But this thing extrapolates up way up here and actually extrapolates to 25.7 Tesla. Yeah. This is temperature, and this is H, mu naught H. Yes. Can I hear the question again? The reason this curves over is all sorts of possible physics. It could be Pauli paramagnetism. It's because the Landau Ginzburg theory only works near to Tc, and all these things. It's only an estimate, right? Okay. When this gradient here was first observed at 1 Kelvin, it was thought to be so improbable that the experimentalists decided it couldn't be intrinsic. And they put their samples away, and they were abandoned for 10 years. Okay? This was first seen in 1973, around the same time that superfluid helium was discovered. And we now know it's one of the earliest heavy fermion superconductors. The reason that this gradient here is so very, very large, it turns out, is because the mass of the quasiparticles is very, very large itself. Okay? But anyway, so in this system, mu naught dHc by dTc is 25.7 Tesla per Kelvin. Tc is 0.925 Kelvin, and therefore mu naught Tc dHc2 by dTc is 23.8 Tesla. I guess that should be 23.8. Extrapolation there, okay? Which is a huge number for a 1 Kelvin superconductor, okay? So from this, we can then deduce the coherence length, Xi, which somehow is not on my notes because it's on my Xi is then 329 divided by 23.8, Okay, and I don't have that exact number, but let me just assume that's like the square root of 16, which is about 4. I think it's something around 3 nanometers when you get that out. Okay, and HC2 over HC1 is actually 5,174. Mu naught HC1 is 4.6 times 10 to the minus 3 Tesla. Okay, that is a hugely smaller than 23.8 Tesla. You couldn't even see it on this scale here. Okay, and so when you plug that in, you discover into this formula here, you discover that kappa is 110, and this comes out to be 3.7 nanometers, and therefore psi, therefore lambda L is 3.7 times 110, which is 470 nanometers. Okay, and this is mu naught n e squared over m star. Okay, and so that's an example of how you can extract these parameters of the microscopic theory from a simple measurement of the lower and upper critical fields. We heard yesterday from Dimitri that they've measured the upper critical field for magic angle graphene. In fact, rather remarkably, in his curves, it was exactly linear, which I thought was rather fantastic. He noted that the coherence length is actually comparable to the Moiré unit cell. Okay, it's many carbon-carbon spacings, but it's comparable to the unit cell. But we don't know yet what the penetration depth of magic angle graphene is, but very likely this is a type 2 superconductor. Yeah? Okay, so that ends my discussion of Ginsburg-Landau theory. And so now I'd like to jump ahead and start talking about BCS. This is going to, yes, question. Misha.
Coherence length in this compound compared to its lattice spacing?
Oh, it's massive. Well, no, not so much. That's probably 10 times the lattice spacing. Yeah, or 5 times, right? Okay. Yeah. By the way, we still don't really know what makes this system tick. It's probably a triplet superconductor. And recently there are some praseodymium materials which have been discovered which are very similar to it and have the advantage that they A, don't contain beryllium, which is extremely poisonous, and B, don't contain uranium, which is actually not such a big issue. Yeah? This is a deadly compound to deal with because of the beryllium, actually. Okay, so BCS theory, okay? Really, BCS theory was a theory that came about as a result after the Second World War. And the Second World War led to huge advances. In particular, microwaves were developed in connection with radar, and it meant that you could actually go and probe metals and superconductors at microwave frequencies. And so, as I'd mentioned before to you, we're going to first talk about prehistory. Prehistory. This is not prehistory of civilization, prehistory of BCS theory, okay? So, as I'd mentioned before, Landau-Ginzburg theory, Ginsburg was really thinking about it throughout the Second World War, but it was finally published in 1950, and this led to this modified London relationship, not J equals minus QA, but J equals minus QA minus H bar over E star grad phi, which was now gauge invariant, okay? This was Ginsburg-Landau, okay? And the idea of an order parameter, that psi was a macroscopic order parameter. But what was it? And could you take it seriously? Was it physical? In somewhere around 1949 to 1950, another bonus came. The theoretical community had finally gotten its act together and understood quantum electrodynamics. And this was done shortly after the Second World War, and it led to the development of Feynman diagrams. And a German emigre, Fröhlich, was working in Liverpool University, and he realized you could generalize the concept of photons to lattice vibrations, which we of course call phonons. And just as the Coulomb interaction comes from the exchange of a photon, there would then be an electron-phonon interaction, which would lead, like the exchange of mesons, to an attraction between particles. And Fröhlich appreciated this and developed his theory actually while he was on a visit to Purdue University. And I'm just going to draw a picture like this. This, of course, is the famous picture for the exchange of a photon in quantum electrodynamics, but it equally well works for the exchange of a phonon. And this leads to an effective attraction, V effective, of Q and omega, which is basically given by some coupling constant squared times the propagator of the phonon. And when you put all of that together and you evaluate this on shell, which means if this is K and this is K prime, then Q is going to be, Q coming here is then K minus K prime, and on shell omega is epsilon K minus epsilon K prime. And when you put those things together, you get an effective interaction, which looks something like this. It looks like minus G of K minus K prime squared times 2 omega K minus K prime over omega K minus K prime squared minus EK minus EK prime squared. And what Fröhlich noticed was that this is an attractive interaction very close to the Fermi surface. He completely ignored the Coulomb interaction, by the way, in his discussion. Okay, he said, well, if that's screened out, should we imagine? This means that very close to the Fermi energy, electrons will experience some kind of attraction. And this led to Fröhlich and also Bardeen to put together theories of superconductivity driven by this idea, okay? And Fröhlich came up with the idea of a sliding charge density wave. And it was a beautiful theory, and it turned out to be right for sliding charge density waves, but wrong for superconductivity. And 30 years later, sliding charge density waves were discovered, and it's the perfect theory for that. Anyone know why a sliding charge density wave is not a superconductor, why it doesn't accelerate in an applied field? Anyone know? Pinning is the answer. And so if you apply an electric field to a charge density wave, you have to reach a threshold field before it starts to move, okay? And that's the end of the Fröhlich theory. Nevertheless, it did lead to a fascinating prediction. It led to the prediction that Tc would be proportional to the Debye frequency, which is proportional to the square root of 1 over the mass of the nuclei. And so Fröhlich predicted there would be an isotope effect if his theory was right. Okay? And so actually the same year, 1950, two groups in the USA having access to isotopes. This was the first time they actually had purified isotopes as a result of the Manhattan Project. They could take different isotopes of mercury and measure their Tc. Okay? And since the isotopes of mercury have different nuclear masses, you can get enough of a range to actually measure Tc, log of Tc, log to the base 10 of Tc, versus log to the base 10 of m. And the curves that came out of that basically had a very nice fit to -1/2. This work was done by two groups, by a guy called Maxwell. No, it was not James Clerk Maxwell. He'd already died at the National Bureau of Standards. And a guy who, at our lab, we consider to be a hero, Bernie Serin, because he also had access to isotopes and low-temperature physics. And he was a good friend of John Bardeen's. They used to talk on the telephone between Rutgers University and Bell Labs just up the road. this was a great development. Okay? And then an outcrop of radar, a young fellow, a fellow called Brian Pippard, who'd worked on radar during the Second World War, started looking at the effects of microwave radiation on superconductors, and he could measure the skin depth. And he found that somehow the superconductivity didn't switch on right at the surface, but was delayed by some penetration depth, or not penetration depth, coherence length. And he was able to understand his microwave experiments by replacing this local kernel, that J of x is proportional to A of x, by a non-local kernel. And so this is Pippard, Brian Pippard. And so he introduced J of x equals minus Q x minus x prime, A of x prime, d cubed x prime. This was the relationship that he discovered. And once you get a non-local result like that, you wonder, well, why is it non-local? What is this scale? He didn't know what the scale was, but it meant that the current was responding through the medium to an electromagnetic field at another location. Okay? So what was transmitting the information from the vector potential to the current? It meant there was a microscopic mechanism, something beyond Landau-Ginzburg theory. Landau-Ginzburg theory was unknown in the West. Okay? It wasn't actually available until around 1956, where you could read it in the early versions of Landau and Lifshitz. These were published by a guy called Maxwell, another Maxwell, who was actually an emigre from the Czech Republic, from Czechoslovakia. He later went on to become a great newspaper magnate. But anyway, Landau and Lifshitz had a little bit about Ginzburg and Landau theory, Ginzburg-Landau theory in it, and a few people knew about it, but Pippard did not. 1955, Bardeen had quit Bell Labs. He was fed up with Shockley, who was apparently a very difficult man to work with, and he decided that he wanted to work full-time on his pet love, which was superconductivity. And so in 1955, he tried to develop a phenomenology. And one of the things he wanted to understand was the Meissner effect, the coherence length, okay, and tried to understand these things. And he came up with the idea that maybe a superconductor, like an insulator, has a gap in its excitation spectrum. And he called this the gap hypothesis. And he actually used London's arguments, whereby the current contains a paramagnetic and a diamagnetic part. And he tried to calculate what these would do in the presence of a gap. And he came to the conclusion that he would indeed get the London equation. He also pointed out that if there were a gap, then the coherence length would be given by Vf divided by the gap. And so a gap would then determine the existence of a coherence length. Okay? And last in my little list of prehistory, Bardeen started working with a young assistant professor at Urbana-Champaign, a fellow called David Pines, and they started looking at the effects of the Coulomb interaction on the Froelich interaction. How to combine screening and the electron-phonon effect together. And this led to a new retarded interaction, the effective Bardeen-Pines interaction between electrons depending on momentum and Q. and it can be written in the following form. The first term is just the screened Coulomb interaction, where kappa squared is the inverse screening length in an electron fluid into the metal. But they realized that after an electron went by, there would be a response of the lattice. And so in their simplified theory, which is a sort of RPA theory, they had this form here. This was what they came up with. This is the Bardeen-Pines interaction. And what's important about this? Well, this is the screened Coulomb. And this is the retarded response of the lattice. Which, if you set omega q here, was just c times c of sound times q. If you set omega to 0 in this expression, you find that the interaction is actually 0. Okay? So at low frequencies, the interaction is 0, but at finite frequencies, it grows to the screened Coulomb interaction. Okay? And nowadays, we think of this with the following picture. Here is an electron traveling at V Fermi. V Fermi is something like 100,000 meters per second. It's way, way faster than the speed of sound, which is about 1,000 meters per second. Okay? And so what happens is that you have the ions here, which are positively charged. And as the electron goes past, it gives them a nudge, and they start to come towards it. But it takes them, they're ponderous and heavy, so it takes them a long time to actually move in to screen out the electron. And by the time they screen out the electron, it's already disappeared. So here they are coming in, like this. And so there's a track behind that classical electron, we think of it classically, where the ions have come in to screen it. The characteristic timescale for this response is t of order h bar divided by t of order 1 over omega dBi. Okay? And so if you think how far the electron has moved, that's Vf times t. But Vf is basically, Vf is dE by dk, which is basically the Fermi energy times the lattice constant. Okay? And so if you put this together, this is then A times the Fermi energy over the dBi frequency. Okay? Debye frequencies are of order 500 Kelvin. Fermi energy is over the order of 50,000 Kelvin. So you've got here a safe factor of 100. Okay? So this highly retarded response is left behind long after the electron has gone by. And it's that positive background that then attracts the other electrons. Okay? And so this is the cartoon picture of where the attraction comes from as electrons go along. And of course, we now know that Cooper pairs form because another electron following after this one can feel this attraction. And they can then orbit one another as a kind of pair. Okay? So one of the reasons that I put all of these things together is that you can see that for this breakthrough to take place, it required a combination of new experiments and also phenomenology. The microscopic theories that Froelich and Bardeen put together actually were kind of warm-up operations. And we don't know much about them anymore. We don't talk about them. But the phenomenology they did was lasting. Question? Yes? I want to say something here before I take this question. It's very nice for the organizers to ask questions, but the students should be doing it much more than they should. Now, Mark, let me hear your question.
You're saying what is on my heart. I have seen this interaction quite often. And I mean, now perhaps it's now that I realize. There is nevertheless something weird with this interaction term. Because, I mean, the only
Yes.
But I mean, what is important is electron-phonon coupling. So where is the electron-phonon coupling?
It's here. Everything is Coulomb, actually. I mean, we love to separate them out, but electrons interact with protons and ions via the Coulomb interaction. So what Bardeen and Pines actually did was that they basically improved what Pines himself had developed with Bohm, which is we now know as the RPA. They said, actually, RPA is the response of the electron gas to the other electrons, but there's also an RPA response of the plasma of positive ions. And they used they took that, and they'd already calculated that, in fact, for electrons, so they just changed the parameters and looked at it in a different regime of parameter space. Okay? And when they put that together and added the two polarizabilities together and put them into the Coulomb interaction, this is what they got. Okay?
So, I mean, what is, it's not only what is in the square bracket that is, so to say, the RPA.
Yes, this is kind of G squared here, yes. And in fact, you can see something interesting. Because you've got an omega q squared on the top, this coupling constant is proportional to q. And that's the response, the interaction of the electrons with the longitudinal fluctuations of the phonons, okay? And so this line of development was just as important as the BCS breakthrough, okay? Great breakthroughs like this are a community project. The Nobel Prize went to BCS. They got the big badge. You get a red badge that says, I'm a laureate, when you go there, okay? But in fact, this community did a tremendous amount for the field, okay? So this was the backdrop. This was the fabric. And Bardeen assembled a group of two others to join him, one of whom was Cooper, who brought the know-how of the new quantum field theory, which Bardeen wasn't familiar with. And the other was Schrieffer, who had been recommended to Bardeen by John Slater at MIT, where he'd been an undergraduate. And one of the first things that Bardeen did when Schrieffer arrived, saying he wanted to become a theorist, was he sent him off to work in a lab, okay, just to get used to the real thing, okay? So let's talk a bit about what came next, okay? And so following the Sordi technique, I have listed my dream list of things that we're going to do, and we've so far done one, prehistory, okay? Good. So I want to talk about, there's going to be a sequence of sketches that come now, okay? And the important thing I want to talk about is a Cooper pair. Because we talked about Landau-Ginzburg theory, Ginzburg-Landau theory, and we've recognized that we need some kind of boson there. But electrons are fermions. They can't condense. And so the only way they can do anything resembling condensation is to combine in even numbers. And the simplest even number combination they can make is a Cooper pair, a pair. And so let's look at the Cooper pair, the Cooper wave function. Let's create our own pair. Okay? And so here are our two electrons. We're going to pair them up. Here is electron 1. We're going to make a singlet state. So this one is at position X. And then here's my other electron, position X prime. And they're sitting in a wave. Let's draw that wave. It's a wave centered around their center of mass. And that wave is, I'm going to draw it like a wave, but really should be simpler than this, but I'm going to draw it like a wave with nodes just for fun. Okay, here is my wave. They're sitting inside. And this means there's a wave function, phi of x minus x prime. This is not the phase. This is that ambiguity of notation I'm sorry about. That's the wave function of the Cooper pair. It gives me the amplitude for finding this one at position x and this one at position x prime. Yes, question?
Before you erase the
Yes.
I don't quite understand why you claim that this is so significant in comparison with BCS. I don't see any pairing. I see Coherence that appear because you have a lattice distortion.
Yeah.
But it doesn't quite complete the loop.
No, but the point was that there was the realization that the important low frequency part of this had an attractive component. So this got them into thinking, well, let's just model this by the simplest cartoon we can possibly imagine. Some kind of attractive interaction, okay? And we're going to assume that that attractive interaction is given by this guy at omega equals ek minus ek prime, and q equals k minus k prime. That was their model, okay? And maybe they thought the details don't matter, and in fact, they don't matter, okay? And so they started thinking about attractive interactions. In fact, it wasn't really until the early 60s or the late 50s that the community got back to thinking about the Coulomb interaction that had been sort of put in here and then argued, well, you don't need to worry about it, forget about that term, let's concentrate on this, right? Okay? What would an attraction do? Okay? And it was very important because it gave you the idea that there'd be a retarded attraction. And Bogolubov, after all, had invented all the machinery needed for all of this in the early 50s, but he didn't apply it to electrons. He even thought there might be some kind of pair condensation, but what the hell, electrons don't have any pair condensation. This is not a very good argument, because he could have thought about other fermions that do have an attractive interaction, such as nucleons, and done it for that, but he didn't do anything, in fact, right? But anyway, so here is the singlet. In fact, in order for this to be a singlet, to make this a singlet wave function, this has to be symmetric in x minus x prime. The spin wave function is anti-symmetric if this is symmetric, okay? And so we can now create our Cooper pair. Our Cooper pair is created by a great big capital lambda dagger. This is the pair creation operator. And what it does is it adds two electrons, operator, in a singlet state with this wave function. Let's now write down that operator. So we have it. Here he is. It involves integral over all possible positions of the two electrons times the wave function that only depends on their relative separation. They are bound together by some force. And now we'll create an electron at position x and create another one at position x prime. And there we are. That's it. These are the creation operators. They anticommute with one another. Okay, this is a singlet. Okay, this is a composite boson. Some people think the Higgs boson is a composite. We know it has a coherence length, but we don't know what it's made of. Technicolor is the extension of this idea to particle physics. And they've tested it out, and it doesn't work. Okay. All right, so let's now look at this in momentum space. And to do that, we have to Fourier transform this guy and write it as a sum over its Fourier components, e to the I k x minus x prime. Okay. Now, condensed matter physicists love to write sum over k, whereas particle physicists like to do integral over k. Right? And this is just a difference in philosophy. If you put your system in a box, which after all would be your crystal, then of course that box has periodic boundary conditions, you might imagine, and that means all the k's are discrete. And it's much easier in your head to visualize discrete sums than it is to actually do continuum sums, okay? Legally speaking, I need to put a 1 over the volume into this to normalize it properly, okay? And then this becomes d cubed k over 2 pi cubed, but I'm going to set volume to 1, just so I don't have to worry about that. So if I now put this into here, if I now put that into there, then I can now rewrite this. I can rearrange the integrals and the summations and rewrite the Cooper pair operator, pulling that sum over k outside, and now putting the first integral over x here, pulling out this e to the I kx there, and putting in my creation operator like that. And then I'm going to take the second integral over x prime, e to the minus I k dot x prime, and then psi of x prime down. Okay? That's the same thing here, or I've got to put my phi of k here. Okay? And now I can recognize that this guy is the creation operator of an up electron at momentum k. And this guy is the creation operator of a down electron at momentum minus k. And so you can see from this little manipulation that we've successfully converted the Cooper pair operator into momentum space, and it looks like this. Normally we work in momentum space, but it's easier to visualize it in real space. Okay? And by the way, this simple picture, which was forgotten for many, many years, was brought back into significance by Phil Anderson when he introduced his RVB theory of superconductivity. Because he said, well, look, actually, a valence bond in an insulating antiferromagnet is rather like a Cooper pair, and I can think of it as being a bit like this as long as I project out the states of single occupancy. Right? So this is, furthermore, this is an entangled Einstein, Podolsky, Rosenberg pair of electrons. Okay? They're an up, down, minus, down, up. Okay? So this is an entangled state, and it's going to be entangled over the coherence length. The coherence length of aluminum is something like 500, half a micron. It's immense, okay? So that's entanglement over a long scale, and then we're going to make the entanglement even better because we're going to put this Cooper pair into a condensate, and we're going to make that phase coherent over miles of dirty lead wire, as Anderson put it, okay? So this is a massively entangled quantum state we're going to make, okay? And how are we going to do it? How are we going to condense the pairs? Bob Schrieffer used to always talk about the rules that Bardeen put before them when they discussed superconductivity. And one of the things that Bardeen said was that you've got to look for something that is a typical state. So now Cooper took this guy and just did the simplest possible calculation. He said, look, Bardeen actually suggested this calculation. Take a filled Fermi C, Fs, and just add one of those guys to it and calculate the energy. Okay? We're not going to do that calculation of the energy. The most important thing that went into that calculation of the energy was the matrix element that scattered the electrons. And in this calculation here, since this just involved pairs, the electrons were always in a zero momentum state, and so you just needed to wonder how k and minus k would be scattered to k prime and minus k prime. And so this is, yes?
Yes. I was going to ask, so you were just emphasizing the long-range nature of the entanglement.
Yes.
Superconductors. Is that what's responsible for the strong success of Landau-Ginsburg theory without fluctuations?
It is in a system with a very long coherence set. That's right. It is indeed. Yes.
Okay, so you don't need to consider those fluctuations.
Well, you do need to consider them, and they're extremely small. So there is a so-called Ginsburg criteria for when the fluctuations are important, and that criteria, which is not in my head at the moment, basically when you work it out in superconductors gives you an extremely narrow region around Tc. So that if you look at the specific heat capacity of helium-4, it has this great big lambda peak. The specific heat capacity of a superconductor actually has exactly the same lambda peak, but to see the lambda, you have to go so close to Tc, you never see it. Yeah? Okay, good question. So here's one of the pictures you might want to have in mind. Here are two pairs, and here are two other pairs. Here is one at k prime and k prime and minus k prime. What's my picture say? This is minus k prime down. This is k prime up. And they are paired together here. And I can think of this pair, Ck prime up, C minus K prime down, acting on a Fermi surface. It's basically a pair above a Fermi surface as K prime P. And all we really need to know is how the matrix element between Kp of the Coulomb interaction or the Bardeen-Pines interaction and Kp prime. Okay? And so the suggestion was just to call it VKK prime. Okay? This is a key step in the BCS thought process. Simplifying the interaction one step further, all you need to know are the matrix elements that scatter one pair into another. Okay? In fact, they took it one stage further than that. They said, well, look, we know this is attractive at low energies, and it's actually repulsive at high energies, but let's forget the fact it's repulsive at high energies, and let's just replace it by a very, very simple interaction, VKK prime equals, well, it's zero. It's attractive at low energies, so we write it as minus G naught for electron energies that are less than omega dBi, and zero otherwise. And so if you think of these guys as being, these are very, very close to the Fermi surface. Here's the Fermi surface running round like this, and in Cooper's calculation, this was forbidden territory. The only scattering was allowed outside the Fermi surface, and this was within a range omega dBi. So it's like a very thin atmosphere around the Fermi surface. And when he calculated the energy of the ground state, by the way, to make this normalize, you have to divide by the volume. Okay? And when he calculated so this thing here was sum over phi k, Ck up, C minus K down, acting on the ground state, which is sum over phi k, Kp. And so, of course, electrons coming into this problem, if you have an electron pair, it has a energy, the heat bath energy of 2 mu, okay, twice the Fermi energy. And he found that this Cooper pair had a lower energy than that the pair came in with an energy which was beneath here. And this gap here, this was at minus twice omega dBi times exponential of minus 2 over G naught times the density of states per spin of the electrons at the Fermi surface. That's what he found. That's what they found. Okay? And this is rather interesting because if you've got a pair sitting down here, okay, this pair is a boson, and it's a very, very diffuse, huge object. So you can put more pairs of electrons into that. Here just calculated one pair. But the obvious question that came next was, well, what happens if we put a lot of pairs here? For political reasons, partly, and also because the size of this pair was immense and strongly overlapping, it became verboten in the BCS collaboration to ever refer to this as Bose-Einstein condensation. This was pair condensation, a completely different thing, okay? Right? Nevertheless, in fact, we now know that this is just a question of where you are in the phase diagram. If you have very, very strong attractive interactions, what actually happens is that pairs first form, and then they condense later. And that process really is like Bose-Einstein condensation, and we can even tune from the one limit to the other in cold atom systems nowadays. Okay? And so it took them a long time to figure out how to go from one pair to many pairs. What's the right wave function? Okay? And this subject had also been thought about in the context of meson theory. Mesons are also bosons, and in fact, one of the things that Bardeen did was to send Schrieffer off to particle physics conferences to get ideas. And he went to one in Hoboken, New Jersey, and listened to lectures on coherent states of mesons. And according to his own description, he said on the way back on the PATH train back into Manhattan, I had this idea that I could use the same kind of wave function for electron pairs, for Cooper pairs. And so let's look at what that wave function was, okay? Well, the obvious thing you can do is instead of having just one, you have n of them. A lot of them. Yes, question. Did I miss a question? Yes. Yes.
So now I see how two single electrons will make a pair. But the question is that if two electrons will shoot each other.
Well, in this, it was just electron here and this electron there. We drop them onto the Fermi surface and they pair up, okay? But I think the answer to your question is it's not which two electrons. All electrons are identical, right? So the question really was, how do you go from 2 to 10 to the 23 over 2, or 10 to the 23 electrons? How do you scale this up?
Because they are not distinguishable, so there should be something like, some factors behind it which
Yeah.
show that they are not.
Yes, but that's true. But by using these creation operators here, all of the statistics are taken care of in the anti-commutation algebra. So the beauty of using the second quantization approach rather than using anti-symmetrized wave functions is that you can just go ahead with the machinery and let it take care of itself, okay? So that if I now take 2 or n pairs and act them on an empty state, you're guaranteed that this is a ground state that satisfies the canonical anti-symmetry properties of the many electron wave function. Yes? This is now going to be no electrons, it's the true vacuum. So in contrast to the early calculation by Cooper, where this was acting, this should have been on the Fermi surface, Fermi C here, okay? This is now the true vacuum here, okay? And this is the BCS wave function written in a way that you're not familiar, okay? And in fact, yes?
So if we did an analysis of, say, I could make a singlet out of 4 electrons,
Yes.
is that just going to be less energetic in favor than pairs?
Well, actually, no, it's going to be more energetically favorable than one pair, in fact. And the way we'll see that is that we won't just do 2 pairs, we'll do 10 to the 23 of them, okay? So
No, I don't mean more pairs. I mean, if I made a bound state of 4 spin.
right, how would you do that calculation? I don't think I would know the answer to that. It would be very difficult. I mean, of course, the question really would be whether that state would split up into 2 pairs or whether the pairs would mold together into something different to that, okay? And I think in the context of the simple model that we have, we can show that this is the right ground state that we're going to come up with, okay? Simply because this simple interaction is so simple, we can actually solve the problem exactly. Yes? So the answer is that I haven't done the way to answer that question is to solve this problem exactly and get the ground state and see it's made up of pairs. I think that's perhaps the right way to deal with it. But let's look at what happens if we pair condense these bosons. Thinking of them, it's ridiculous to think that they're non-interacting because, of course, they strongly overlap. But we can at least, nevertheless, put pancake along atop a pancake and make a macroscopic state and look at it. Okay, so let's look at it. Now this state here is n bosons, right, basically. And since we've got a very, very large number of bosons, we might as well work in the grand canonical ensemble rather than in the ensemble of definite particle number. And so instead of doing this, let's look at the typical state, the coherent state, that looks like that. Okay? These aren't the same because this contains n and n plus 1 and n plus 2. This is, of course, the sum over okay? Right. And in fact, in contrast to this one, this actually has, this is like a wave packet in many particle space, right? Just as to form a wave packet of waves, we make a coherent state of position and momentum. This is a coherent state of lambda, and in fact, we won't deal with it in this way. We'll, in fact, this is the BCS wave function written out in a form that you're not familiar with. Let me now show you this is the BCS wave function. Okay? The BCS, of course, we might want to project the component of this with a definite number of particles. We can do that, but let's just deal with this state for the moment. Okay? So now let's plug in the fact that this lambda operator is just the sum over all pairs weighted with phi of k. And so this then is equal to exponential of exactly that. There it is. Now, the beautiful thing about this exponential here is that it's diagonal in momentum space. And so since the operators at different k commute with each other, or anti-commute with each other, the lambda, these guys at different k commute with each other. And so we can actually write this as a product over k of the individual operator. And now, if we look at this exponential and start expanding it as a power series, the first term will be 1, the second term will be 1 pair, the third term will be 2 pairs, but it simplifies because ck c minus k squared is 0. In fact, to any power r, where r is greater than 1. And so this quantity here just truncates at the leading order. It truncates as 1 plus phi of k, ck up, c minus k down, plus 0, plus 0, plus 0, plus 0, plus 0, plus 0. In other words, forget about everything else. And that's what it is. Every single step here is an identity. And so, in fact, you can write the BCS wave function as a coherent state, or you can write it in this product form, which is the familiar form of BCS. BCS normalized this wave function. This is not a normalized wave function. If you take the product of this with itself, then you'll see that for each k, we get 1 plus phi k squared, mod squared, if it's complex, product over all k. And so to normalize this, it's better to divide the whole thing, each term, by the square root of 1 plus phi k squared. And you then define u of k to be equal to 1 over the square root of 1 plus phi k squared, and v of k to be phi of k over the square root of 1 plus phi k squared. And you can then write your way, and by the way, the phases don't matter here, but actually I'm going to put minus here, just so that you don't have minus sign problems later. And the normalized BCS wave function is then phi of k, u of k, plus v of k, c minus k down, ck up. And this is the wave function that Bob Schrieffer came up with as he took the PATH train from Hoboken to downtown Manhattan. And according to his memories, he worked through most of the night and had all the basic key results out by the early morning, okay? Meaning he had the energies and maybe he had the quasiparticles, yes? It can, yes. Didn't I put mod here? Oh, you're right. It's, yeah, well, I think that's right. 1 plus mod phi k squared. Oh, yeah, here. Yes. There. Yes. By the way, once you've got this, you can actually get back to this guy. Okay? And this was first realized by Anderson sometime later. He pointed out that if you act on the state e to the I alpha times the number operator of the electrons on BCS, then what happens is that this gives you U of k plus V of k e to the 2I alpha C minus k ck up, because each time you do this, each creation operator picks up a power alpha. And so this is the state alpha, and you can now pick out the components with a number of pairs equal to alpha simply by taking this state alpha and Fourier transforming it with an e to the minus. You want to have exactly, you want 2 alpha to be, I'm going to get my knickers in a twist here, e to the 2 alpha. So what I really want to do is put an alpha over 2 there, put an alpha there, and call that alpha. And if I now do a Fourier transform over alpha n, like so, I get back this quantity with the appropriate normalization. Okay? And so, actually, since the energy of this state won't actually depend on alpha, all you have to do is to take those degenerate states, each with exactly the same energy, and Fourier transform them over their phase, and you can project out the original state. Okay? But it's much, much easier to do your calculations with this, and it's also much more physical, because this is the state which has the phase coherence manifestly shown to you. Okay? Yes. Yes.
That remains a stupid question, but when you're going from like the exponential form to the product form, right?
Yes.
Shouldn't there be some residue from the commutation relations, because you cannot just split up like the operators with product? Like, did you use some bigger couple Hausdorff stuff in there, or?
Nothing. I didn't use anything fancy. Which step was the fancy step? Look.
For the second to the first step.
From there to here.
No, the next step, right?
There to there.
No, that's to the next step, yeah.
From this one to that one. This is perfectly okay, because ck c minus k commutes with ck prime c minus k prime for all k and k prime. So there's nothing fancy at all. There's no Baker-Hausdorff here. Okay? Sorry. For going from here to here. Yeah, that's probably the really creative step. Okay? And so I think the point is that actually using this the point is this thing here has a very, very sharply peaked probability distribution around n. Okay? But it's easier to calculate with this coherent state, which lives in the grand canonical ensemble, than it is to work with the... See, this spans the Fock space. This is in one slice of the Fock space. So this really feels the phase coherence between the states of different n. This is also the state where there is a expectation value for the pair operator, right? Okay. So this is a little bit like going between position and momentum space in some sense here. We are going from definite x to definite, x is like particle number, to definite p. Okay? So this is truly BCS started out with this guy here, okay? And it was a very creative step that they did. So the idea that a condensate is better treated in a state of indefinite particle number was something that came from meson physics but was adapted to superconductivity by BCS. BCS didn't even do this first step. They started here. I'm trying to motivate it and connect it up with the connection between the original Cooper state and the many particle state. Right, so the point is, here's the point. In the thermodynamic limit, the properties are extensive, meaning meaning the local properties don't depend on the volume of the system or the number of particles. They just depend on the ratio of n over the volume, okay? And so actually, as long as you're dealing with a thermodynamic limit, it doesn't matter whether you deal with n pairs, n plus 1 pairs, n plus 2 pairs, or even a distribution of pairs here where the root mean squared, delta n squared, is of order n. Is of order the square root of n, right? Because the square root of n is 10 to the 11, whereas n is 10 to the 23. So the width divided by the separation is 10 to the minus 11. You can't see that. That's way smaller than the thickness of a piece of chalk, okay? And so the point is that for intensive properties of the superconductor, it should be perfectly okay to average, to take a weighted average of nearby states with different numbers of pairs. And the simple weighted average to take is the exponential. That's my best effort in answering your question.
Yeah, I'm just trying to tie this to what you're doing later. So now we've established that we've done some kind of expansion in this different set of states, different number of particles. Then what do we do at the end over there? We're multiplying by some global phase with Fourier transform back to their equivalent.
So you're okay here, right? Yeah. Right. So it's just demonstrating that if you now project, this is just translating the phase of the wave function, okay? So just as a momentum operator translates the position of a particle, the number operator translates the phase of the wave function, okay? And so that's what I did here, okay? Right? And now if you look at the coefficient of the states that have n pairs, it's e to the I alpha n, if you have n naught pairs. Okay? This thing is sum over e to the I alpha n naught times n naught, where n naught runs from 0 to infinity. Okay? Okay, if I now decompose this in terms of numbers of pairs, okay? And so if I now Fourier transform this, I pull out the state with a definite number of pairs. If I put n0 here, then I'll get that state. Okay? It's just the projection. So the projection can be written as an integral over the gauge over the orbit of the gauge group. Okay? Right. Good. So, yeah.
So I'm a little confused because now we're working with the true vacuum. Earlier,
It's the true vacuum. It's the state with no electrons.
yes, but earlier we were showing that the pair combination was mostly just within the divide.
That's right. So now we're going to have to see that this recovers the Fermi surface and a very narrow region with it from the next step. It's not immediately obvious how this would work. I suppose the answer would be that these Ks here, to be strictly legal, would be Ks in the vicinity of the Fermi surface, if you want to think of it there. There are a lot of hidden assumptions to all of this. Okay? Right? Yeah.
Can we also calculate, or do we have any estimations about the lifetime of that creative verb?
Of the lifetime of the.
Creative verb. I mean, how long does it stay?
This is a variational state. It's an ansatz for the ground state of the superconductor, right? So if it is the ground state, it lives forever, right? Yes. Well, effectively, this is what you're going to have. If we ever get beyond this point, which we might not, that's okay, we'll see that what this does is to smear out the Fermi surface. Okay? So the obvious next question is, to understand what this does, you have to do some calculations. Right? That's the next step. Okay? So what we've done so far is we have done this. This is fantastic for me because this is the next 2 lectures. If we won't ever get to the last lecture, that's okay with me, because that's the learning process. Okay. Let's now take this to the next step up. This is the BCS wave function. How do we calculate something from it? It's just a trial wave function at the moment, right? Okay. To do that, we need to write down a many-body Hamiltonian. Okay. Right? And so the many-body Hamiltonian that BCS wrote down was just the second quantized version of Cooper's original calculation. So you may remember that Cooper had this interaction that scattered pairs. And so it took BCS a while to figure out how to write that down in an elegant way and to show that indeed the wave function that Schrieffer came up with was the ground state of that Hamiltonian. Okay? So let's look at that. Okay? So before we do, let me note that this BCS wave function has the property that if I destroy a pair from it, like so, remember psi BCS well, I want this. If I destroy a pair, let me write it like that. If I destroy a pair from this state, I zap out this term here, and I just get a term with a v of k there. And when I overlap that with the state, I get a u of k. So this is actually equal to u of k, v of k. Okay? And so, and by the way, u of k squared plus v of k squared is equal to 1 to normalize the wave function. So that okay. Good. So to progress further, BCS wrote down a Hamiltonian, and here it is. Here is the Hamiltonian. Contains the electrons. This is just the dispersion of the electrons, where actually epsilon k here is not the energy of the electrons, it's the energy of the electrons minus the chemical potential. And this is where the information about the size of the Fermi surface resides, because this is equal to 0 on the Fermi surface. Okay? This is k squared over 2m in the simplest model. Okay? And then the next term is this scattering term that scattered pairs. VKK prime, CK, CK minus K prime, CK prime. Up, down, down, up. This is one of the celebrated BCS Hamiltonians. It's very, very simple. It's a dead simple model, and we haven't described what VKK prime is. Okay? VKK prime will have certain properties. Presumably, it only depends on the angle between K and K prime and how far away you are from the Fermi surface. And so they chose a very, very simple version for this pair scattering term. They chose it to be, as I mentioned before, to be equal to minus G0 over V for electrons near the Fermi surface, and 0 otherwise. In other words, this only acted on electrons very, very close to the Fermi energy. Okay? And the picture that we had before, here is the Fermi surface, and now this can be any set of pairs. Here's K and K prime k and minus k being scattered from k prime and minus k prime. Okay, so up. And this is the scattering amplitude, this is an S-wave interaction. Okay? And so in this particular form, the Hamiltonian can be written even more simply. It's just written, so this is our BCS Hamiltonian. Let's now write it in its S-wave form, epsilon k minus G naught over the volume, and I'm going to write it like this, A dagger A. And A here is just the creation operator for a pair. It's really the same as our pair creation operator, but with phi k equal to 1 everywhere. And this is with the requirement that epsilon k is less than omega dBi. And A is the complex conjugate of A dagger. Okay? So that's what we're going to have to look at. And so, tick. Giovanni's not here. Okay, but he will know. Oh, he is, okay. You know you're famous now. Good. So, now this Hamiltonian can be solved exactly. That's the beauty of it. Okay? And the reason, let me explain why. Let's talk about the mean field theory. Okay? And so this Hamiltonian can be basically solved using mean field theory. And the mean field theory that we're going to solve is basically to give A an expectation value. And we're going to identify minus G naught over V times the expectation value of A. We're going to call that delta, and it will be the superconducting gap. And it will have a phase like that.
Sorry, question?
Yes.
So you define A as for when phi is equal to 1 everywhere. Is this phi equals to 1? Oh, it's only in k-space. No, it's
This is A. It's not my original. It's a different operator to capital lambda. Okay?
for sure, but in your definition for capital lambda.
Capital lambda, which we've now left alone, but we'll come back to, was with a phi of k in here.
Okay, so is phi of k set to 1 everywhere, not
Ye-
phi of x?
Yes, phi of k set to, but
Okay.
that was just an aside. This has nothing to do with lambda. Okay, it's A, right? Okay, right? Okay, so but it resembles lambda with phi of k equal to 1. There's no assumption here. This is what the this is a Hamiltonian. Okay, it's the result of setting v of k prime equal to minus g naught. That's all it is. Okay, right? Okay. So this is a mean field assumption. Let me show you why it's exact. Okay, yes. Yes. V is the volume. Yeah, and yeah, it's the volume. Okay, thank you. Yeah, so so this mean field assumption, I should have written it here. Mean field theory. The mean field theory is that delta, which is modulus times phase, is minus g naught over v times a, which since a expectation value, since a involves a summation over k, we can write this as minus g naught over minus g naught times the sum over k of c k up, c minus k down. What the hell am I doing? 1 second. This is not with the daggers. This is c minus k down with k up without the daggers. Okay. And I can write that in the continuum limit as minus g naught integral for 3 dimensions. Because in the continuum limit, sum over k, 1 over v naught is equal to d cubed k, or ddk, over 2 pi to the cubed. Okay? That's because your momenta are 2 pi over L lmn, and in the limit that big L goes to infinity, the discrete momenta become a continuum, and the summation over k divided by v summation over k becomes v d cubed k by 2 pi cubed. So if you divide by 1 over v, you get this, okay? So why is that a good approximation? What we're basically going to have to think about here is that we have some sombrero energy surface, and here is our mean field theory, but this quantum operator A has an expectation value which undergoes 0-point fluctuations, okay? And these fluctuations are going to give to a root mean squared amplitude of delta, okay? Now, the distribution of deltas is determined by a probability distribution, and that probability distribution function involves some kind of amplitude which depends on the action of the associated with a fluctuation in delta. I'm going to write it divided by h bar, okay? And the only important part about this argument is that this is an intensive quantity, but the action associated with a fluctuation in delta, which is for the whole system, okay, is of order the volume. And so this S of delta lambda, if we think about that in Landau-Ginzburg theory, will go like the volume times R times delta lambda squared in Landau-Ginzburg theory. And the important thing here is it goes like the volume. It's extensive, okay? And therefore, if I look at this distribution function, which is really something inside a path integral, but let's not worry about that right now, it has an exponential of minus delta lambda squared divided by h bar times R inverse divided by v. In other words, the order of magnitude of delta lambda squared is proportional to h bar R in h over RV. And so as the volume becomes macroscopic, the size of the fluctuations becomes negligible. And since this interaction here involves all k in this narrow shell, we can be sure that in the thermodynamic limit, the fluctuations in delta in this specific model vanish. Okay? Now, in a real superconductor, you're dealing with a sum over particles within the coherence length, which is very, very large, and so the fluctuations are still quite small. If you go to a strongly interacting superconductor with a small coherence length, the things I'm saying here become completely inaccurate. But in this particular model, the fluctuations in A are of order the volume. I'm out of time now, but we've had lots of questions, and that's just fine. What I'll do next time is continue this development, and I'll argue that this model can be now rewritten. We can now write, when we write A, we can write it equal to its expectation value plus its fluctuations. This is an exact statement. It's a restatement. And then we can expand this in powers of delta A. The first term will just be A dagger A. The second term will be delta A times A. And the third term will be A dagger times delta A. And the fourth term will be delta A dagger delta A. So far, so accurate, but if we scratch this term, because this term is of order 1, and these terms are of order V, then we can, relative to one another, that means that I can then take this term here and now rewrite delta A in terms of A and expectation value A. And what we'll find is that this expression here can be replaced by its mean field form, which is delta prime A plus A delta plus delta bar delta over G0 times the volume. And these terms here are nothing more than the pairing terms. So we will pick up there tomorrow morning. Okay? Thank you.